Hello, I'm Pawel and I'm a master's student at the Luleå University of Technology over in Sweden. And I'm here to talk about SyncRim, which is this tool that I've been developing as partly my master's thesis and partly a hobby project. So I'll start by covering some of the background, so the tool hopefully makes sense to you. And then I'll tell you a bit about my experience building a simulator like this in Rust, along with some takeaways and hopefully a live demo. And I will wrap up by showing some use cases and tying this whole thing to reality. So SyncRim is a synchronous circuit simulator, but what does that even mean? A synchronous circuit, at least as far as SyncRim goes, is just a collection of components and the connections between their input and output ports. So a component has some inputs and some outputs and maybe a state if it's, for example, something like a memory. And the outputs are just functions of the inputs and the state. So this might not make much sense, so I'll show you a quick example. Here we have a simplified version of a typical program counter circuit. So it's something you might see in an instruction fetch stage of a processor. And the idea here is that we want to increment the instruction address by the width of an instruction on every clock cycle. And in this case, the width is 4. So we have an adder. I don't know if I can maybe point with my pointer. You probably can figure out what the adder is. We have an adder, which is a component that just adds the two inputs. A constant 4 on one of the inputs, and the second input is just the output of the circuit. So let's see if we can figure out what the output is, which in this case would be the instruction address that we forward to the instruction memory. So we initialize the bottom input to a 0. The constant gives us a 4. 0 plus 4 is 4, so the output is 4. But if the output is 4, the bottom input becomes a 4 as well, and so the output is 8, and obviously something is wrong here, and this circuit is invalid. An important distinction to make is the difference between combinational and sequential components. You can see the combinational component as always being evaluated, like our adder, while a sequential component is only evaluated when the simulation is stepped, so we prevent these combinational loops. In this case, we can put the sequential register on the bottom input, which just mirrors the input as the output whenever the simulation is stepped. So here the output of the register is our instruction address, and you can sort of see how the circuit works in the bottom pictures. In a more complicated circuit, we can run into some pretty complicated data dependencies. In this simple circuit, the instruction memory uses the instruction address to produce its output, and so the register has to be evaluated beforehand. If we treat the components as nodes and the wires as edges, we can look at the model as a directed graph. And any topological ordering of this graph will give us a valid evaluation order. And of course, any cyclic graph does not have a topological ordering, so we treat sequential components as a starting point and split the graph along their entering edges. And as a bonus, any graph that is still cyclic after this split is invalid, so we can detect faulty models. So this brings us to SyncRim, which was the inspiration for SyncRim. SyncRim is a synchronous circuit simulator which was developed at LTU, my university, some 20 years ago. It's written in Java, and since the release, it's been used for teaching courses in low-level programming at LTU. So the simulator implements a model of a MIPS processor and is fully open source, but the development has pretty much stopped. And this is a picture of SyncRim. So in the middle here, now I could use the pointer, there we are. In the middle here we have the MIPS core, I guess. To the left is an instruction view, and we can see which instruction is executing. We can set some breakpoints, and we have a data memory view here, so we can sort of see output. And this screenshot, if I remember correctly, is taken on a 1080p screen, and you can sort of see in the view that the font scaling is a bit wonky, and this gets even worse on higher resolutions, which I think this is a 15-year-old Java Swing oddity, but I'm not sure. Right, so some pain points of SyncRim. Firstly, the toolchain we use to compile code for the MIPS model is an old fork of the MIPS GNU toolchain. So it's outdated and lacks support for operating systems like Windows and Mac OS. And this is important because we use SyncRim for an introductory course in assembly programming at LTU. So each year, something like 100 students are using this, and some of them have never touched Linux, let alone a terminal. So assisting them with setting up the environment for this on 100 different setups on each course occasion and staying sane at the same time is borderline impossible. Also, the MIPS architecture, while it's a good entry point for teaching assembly, it's not exactly state-of-the-art, to the point where even MIPS Technologies, so the company behind the architecture, has moved on to designing RISC-Vs. And as I said, SyncRim is about 20 years old at this point, so the people behind the project have also moved on. So there is there is little documentation, so the project is effectively unmaintainable. And because of this, SyncRim is stuck with the MIPS and this 15-year-old wonky Java Swing version. So how do we address this? We thought we can just rewrite it in Rust. So now we get to SyncRim, which is the topic of this presentation. And it's well, basically intended as a successor to SyncRim, but written completely in Rust. So instead of the MIPS, we bundle this simulator with a model of a RISC-V core and some generic components like the adder or the register I showed in the simple circuit. This time around, to compile the user-provided code, we didn't want to rely on some external tool chain. But how can we do that? Essentially, the RISC-V model memory is initialized using an ELF binary, which we disassemble, and we populate the memory with the data and the instructions contained within. But to get an ELF, we need a compiler, so we are back to square one, RISC-V GNU toolchain. It is, or is it? Since we are running a Rust crate, the Rust toolchain is already there, so we thought we can use that instead. We can package the RISC-V model with a dummy crate, move the user-provided code and the linker script into that crate, compile it using the Rust toolchain, grab the resulting binary, and just populate the model memory using that. And all of this is done with a single command from the user and just the Rust toolchain, so we don't need anything aside from that. And my takeaway from this is that for a simple user space application like this, we don't really care about the memory safety features of Rust. Instead, we have Cargo managing a dependency tree with like 400 library crates, and Rust C cross-compiling for the RISC-V target out of the box. So the productivity boost here is pretty massive. Oh, and this picture shows this is basically the entirety of that dummy crate. So here all we do is we emit this assembly file as a global assembly block. And we also have to provide a panic handler to satisfy the compiler. But since we never call it from the assembly, it's optimized out. Right, so now I'll hopefully show you what running SyncRim or SyncRim looks like in practice. And for this, I can escape. Right. Yes, so it's just cargo run. We point it to the RISC-V model. In release mode, we give it an assembly file and a path to the linker script. And here we have it. And it's much the same as SyncRim. Let's see if I can zoom out a bit so you can see the model. Ah, it's a bit sensitive. Sorry. Yeah, maybe I'll just move them out of the way and you sort of get the gist. So it's kind of like SyncRim in the GUI department. You have your instruction memory highlighting which instruction is executing. You have a data memory and a view of the registers. And if we, let's see if I can find the end flag. Is that it? I hope so, yeah. And we run the simulation. After a while, we can see that there is some Shakespeare output in the data memory. This is a kind of an infamous lab at the LTU, which I ported to the RISC-V. Let's see if I can find the slide. Start from current, yes. Now, as far as the GUI goes, to address the stuck with Java Swing issue, we chose to completely decouple the simulator backend from the front end. And this allows us to experiment with using different GUI frameworks without changing the underlying implementation. So at first, we were focusing on a Visia-based interface, but since then, I've personally moved on to using eGUI, which Per was using for his cut creator crate. And my takeaway from this, at least, is that it seems using Visia, it's easier to get exactly what you want, while eGUI provides a quick way to get somewhere in that ballpark, and you can just move on to other issues, which is nice when you're just trying to get it out of your way. This decoupling of the front end and the back end also opens up a possibility for running in headless mode, so without the GUI. And I'll talk about the possible application for this later. And we also provide a graphical way to design models with an editor, so I think it's a quick way in to just start experimenting with the tool. And this is a screenshot of this editor mode, so you can sort of drag. It's in horrible resolution, but you get the gist. You can sort of drag the components in from the left side into the view and connect them with wires. And there's, of course, also a way to do this programmatically if you don't like the GUI. So, although the use case for SyncRim has mostly been education, there's potential to go beyond that with SyncRim. If we consider the RISC-V architecture, we have an open ISA, which allows smaller companies to manufacture their own cores with custom features. But prototyping these takes a lot of time and effort. So tools like SyncRim offer a much higher level of abstraction. Components can be implemented and integrated really quickly, so there is room here for some hardware-software co-design experiments. As an example, we have the click, which is an interrupt controller. And to give some background, if you're familiar with embedded Rust, you might have heard of the Arctic framework, maybe, which is essentially a real-time operating system, first developed at LTU, but now it's more of a community project. And it's widely adopted in the embedded Rust community. So Arctic leverages on the Cortex-M interrupt controller to accelerate scheduling of tasks. And because of this, it's incompatible with RISC-V microcontrollers. When exploring ways to port Arctic to the RISC-V architecture, we quickly came to the realization that the interrupt controller, or the standard interrupt controller on the RISC-V, is too primitive to support this Arctic acceleration scheme. There is a specification out there for an architecture extension called the click, which solves the issue, but it's hot off the press, so there's no actual microcontrollers packaged with the click. So instead we decided to implement it for the SyncRim RISC-V model, so we could start exploring how we would port Arctic to this emerging architecture. And so implementing this component took like a couple of days, and now we have a Rust click driver and an Arctic port ready for testing for when reality catches up. And actually, last evening, I found this really obscure Chinese manufacturer that are claiming they're packaging their chips with a click, so maybe I'll order that and we will see where that goes. We have. The same company has made a fork of QEMU, which implements this obscure chip, which I was trying to get to work yesterday, but I didn't quite finish it.
Excuse me, here's a microphone.
Yes, sorry.
Here's a microphone for questions. Just reminding you guys. Thank you.
So the question was which company, and it's T-Head. So it's a subsidiary of Alibaba, and this you might have heard of. Right. Another example is Antic, which is a hardware-accelerated priority queue proposed by Antti, who's here somewhere, I think. Yep, over there. And it allows for constant time push, pop, and drop operations, which is interesting for us Arctic folks because we use timer queues to schedule future tasks. So during the fall, Antti visited us in Luleå for a couple of days, but the issue at the time was that Antic had just been presented a week prior. So there was still a long way out to having a real core integrated with it. So during his visit, we implemented an Antic component for SyncRim, and we could start playing around and exploring what could be done with it. Right, so when Per first presented SyncRim in Helsinki in June, I was unfortunately not present, but I know what it looked like. At that point, it was about a month old and just had a bare bones Visia GUI and some proof of concept examples. So in other words, we've come quite a long way since then. We now have a working and tested RISC-V model and a decent, I would say, graphical user interface. But there's still a lot to do. The headless mode I mentioned earlier is not implemented, but would open up the possibility for integration of SyncRim models with CI. So you could use SyncRim to simulate architectures which you don't have QEMU models for. So, for example, this click-equipped RISC-V. And in this case, a debugger component would be of use. So you could connect to the simulated core using GDB. And I have a proof of concept for this, but not much more. And of course, we want to add more models. There's just never enough. So to wrap this up, the project is fully open source and available on GitHub. So go on and check it out if you're interested. And please use this branch. It's the most up-to-date, so this eGUI inst data. And thank you for listening. And do we have any questions? So we have over there.
You were mentioning about the potential applications of the headless version. Have you thought about using it like for the recent validation projects that have started for validating the CVA6 and more? Like, do you think these could be used to simulate like high complexity
I think
models?
Yes, probably, but then you would sort of need to port the model to this new framework, and of course there can be error in between. There's no way to generate these models, so that's like another.
In your example code, you use assembly directly included to the binary.
Yes.
Why don't you use RISC-V RT crate? Is it incompatible with the platform or what?
Why I don't use the RISC-V RT crate? Well, that's a Rust crate, and so the example was just an simple assembly example, but we do run Rust crates using the RISC-V RT crate. Okay,
yeah, and the other question, I was a bit surprised that you only mentioned click, because from what I recall, in one of the first microcontrollers on RISC-V, there was already a click interrupt controller, yes, which is more powerful and it has priority, so it looks like it can be suitable for Arctic, for example. Yes, and there is a way to map Arctic to the PLIC, but it's sort of complicated, and I don't really remember what the issue was there, but maybe Per knows this off the top of his head. Do you?
I'm actually an expert on this particular subject, but I don't recall either.
Henry also knows this, probably.
Do you have any idea?
No, you can go ahead. All right.
I don't remember. I think Blick has it has the threshold register and it has priorities. And What else do you need? I think there was a third thing that we also need.
We wrote a paper on this, on mapping Arctic to different interrupt controllers, and the plick was feasible, but there was some caveats, I think, that I don't remember.
I don't think we targeted the PLIC in the paper. I don't think we analyzed it in depth.
But my understanding is that it's intended for multi-core usage, and that it's not really a local interrupt.
Okay, I remember now. So the PLIC, what it usually does is that it multiplexes a bunch of external interrupts to a particular core. So I'm not sure if it like, I mean, from the hardware point of view, I think you effectively have one interrupt, and then I'm not sure if you do software dispatch or whether it delegates to CLIC to do the rest of the processing. But I think the PLIC operates on the wrong level in some sense, but we'd have to take a look at the spec and like revisit the issue.
And maybe could it be that the plick doesn't support raising interrupts programmatically, so you can't set the pending flag from your software, which sort of ruins the idea of software tasks if you know how those work in Arctic.
I think it was a little unclear in some of both the CLIC and the PLIC specification. I think it was sort of left unsaid if you can raise them, because it's.
Well, in the click you can. It's sort of.
Okay.
Yeah.
So at least on ARM platforms, it's like given that you can raise any interrupt from software. Even hardware interrupts, you can raise them from software, which is of course useful for testing and for, I guess, delaying the dispatch of an interrupt or something like that, or like delegating to software or whatever. But on RISC-V, it's not always like that.
Yeah. So I hope that answers your question a bit at least. Any other questions? Yes.
Does the CPU model in the simulation work on the kind of gate level simulation, or is it like a separate block that's hard-coded to just magically do something within the Rust and then produce the values for the next iteration?
Maybe I can show if I close out of this. No, not out of LibreOffice, but SyncRim. Yes. If I LVM here, let's see. Components, and let's see if we can find a simple one. Maybe actually maybe the register file. So basically this is one of the components, so this is the register file. And so you have some internal state, some input ports, and then there's some output ports as well. And all it does is sort of implement this component trait, which consists of a single, or pretty much a single function, which is this clock method, which is called by the simulator on every clock cycle. And so what it does is sort of get its inputs, do some Rust magic to calculate the outputs, and set the outputs. So here we, I guess, check the right enable, we check the right address, we modify the state, we see if there's a read or a read address, and we set the read output to the sort of requested register. Does that answer your question?
Yes. I also have a follow-up question that's somewhat related or not. I've been also playing with the idea of these simulators, but never got to finish any of my ideas. But one idea would be that if you get like a really complicated model that has plenty of ports and it gets slow to simulate, then you could basically double buffer every wire in there and then just accelerate with the GPU or something. Have you thought it would? Then you wouldn't need to figure out the order to evaluate or anything like that.
That it needs to.
So it would kind of evaluate every block in parallel and then get the next state and then just double buffer that? Have you thought about it?
Yes, we've been sort of discussing this, but we haven't really done anything in that direction.
I can just comment a bit. The idea is that it's completely up to you at what level you want to model. The register file here is modeled at the RTL level, but you can also hide internal state. So if you have something that is really, really complex, you might implement the state machine and so forth directly in Rust and just have a sort of a high-level model of your underlying hardware. Enough for doing simulation, but it's not really reflecting the exact internal state updates that you might have in an RTL model of it. Or at least you're hiding it from the end user. And since we are using Rust, and Rust is fairly good at optimizing code, we haven't seen any performance issues. It's more like the performance issue is more about the usability and the graphical user interface. And we haven't, this is not intended, at least for now, for running Linux inside of the simulator. That's not our target. But at least to be able to evaluate like this architectural extensions, it's very, very fast to come up with a new extension or a prototyping. The click was a couple of days. Yep. Prototyping Antic was also just a 2-day effort. So in comparison to writing HDL code for the same thing, I think this is much faster. And you can directly run program against them. Otherwise, you would have to do some very later interaction, and it's not so easy to simulate software onto very later as it's to do it here. Yep. So I think that maybe gives a bit of background to what the intentions are. But since it's an open source framework, and this is truly open source with an open source license to it, so it's just for anybody to.
I don't know if we've actually decided on a license, but it will be free and open source.
Yeah.
And all
it
of
is
that,
open
so,
source,
yes.
but and it will be free, so it's not contained in any way. Yes.
You were showing the code just now, and so you're passing the mutable simulator through to every call and so on, and you're doing like get input value, set input value kind of things. So what is kind of the heap structure of your simulator, or when you are getting a value for your input, or when you're writing your output, where is it actually kind of stored? What kind of structure does the simulator hold for it?
That's a good question. Don't remember. It was a long time since I touched the actual simulator backend. Let's see if we can.
As of now, we have been experimenting a bit with how to do this, and this is a very quick and dirty approach to it. The simulator itself holds a global state. So everything is just stored as just U32s. There is nothing else. So there is no typed data inside of the simulator. In the next revision, we might look into instead letting the components host the data. And that would allow us just to use a trait for getting and setting in a more controlled way, meaning that you could not accidentally connect the wrong typed port to, well, it will be a type error if you try to do something like that, because then we would have a try into and it will fail. So this is not done, and the proof of concept state that we have now is sufficient for our needs, but we are always looking for improvements.
So the global state, how is it actually? Is it just like a hash map of the
I think it's a hash map.
Yeah.
Yes.
So this is currently just a simulator. Have you considered maybe adding possibilities to do like a hybrid approach of like maybe grabbing a logic analyzer and a physical chip and put some leads on some lanes and analyzing or simulating or doing a combination approach of software and hardware?
I don't think I follow. Can you?
So would it be possible to step through some things on actual hardware and visualize it with the simulator as well, or do a sort of combined approach between hardware and simulation? For example, you have the component model here so that you can have these inputs and outputs. Could you, for example, add some hardware components where that signal goes to and then comes back to your simulator?
Yeah. Or comes back to your simulator. We haven't really thought about it, but it would be possible. Yeah.
Okay. Yeah.
Once again, I can comment a bit about this. We did something similar when it comes to SyncRim about 10 years ago, or maybe it was more like 15 years ago. We had a simulation toolchain running in parallel, in tandem with SyncRim. So we were interacting with that in order to have HDL models that were simulated, co-simulated with the SyncSim module. Or models and allowing like visualization for actual HDL. But we dropped that because our Europractice sort of contract went out, and it was very, very expensive to get these mentor tools at that time. And I think now with tools like Verilator, it's probably feasible again. I haven't looked at interchange format in between, how you would interact with the Verilator. Because Verilator does some things very good because it starts from real HDL. Here we can, as I mentioned, abstract further if we want. Yes, sorry.
Great. So we'll be switching the speakers to the timetable, and for that we'll have a short technical break, apparently just a couple of minutes as we rewire the next person. So I think it will be Vadim next, right? So you're up.
Thank you for the questions and for listening.